Next, we shall discuss about the determination of calorific value of any particular fuel. It might be a solid or a liquid by using a bomb calorimeter. How this experiment works and how we need to construct this experiment, and during the construction what are the things we are using, and how the fuel will get ignited and how the liberated energy will be calculated. Okay, so along with that we shall come out with the expressions to calculate the gross calorific value and net calorific value. Okay, yes, so now we shall go for the determination of calorific value of a given fuel sample by using bomb calorimeter. So this is a very simple experiment which can be used to determine the calorific value of only solids and liquids, because it's very tough to hold the gaseous fuels inside a bomb calorimeter, because we have to maintain such a high pressure and conditions are not satisfying for using the liquid fuels in case of bomb calorimeter. So hence today we shall take up some solid fuel, or it might be a liquid fuel, and the known mass of the fuel when it is burnt completely in the presence of oxygen, how we can determine its calorific value by using bomb calorimeter. Okay, so the instrument name we call it as a bomb calorimeter. So coming to the construction part, first we need to discuss about construction of bomb calorimeter, and then we need to go towards the working of bomb calorimeter. So how it can be constructed here? See, bomb calorimeter, it mainly consists of a stainless steel container. It mainly consists of a stainless steel container. Okay, it is completely coated with insulator, because whatever the heat that has been generated during the combustion of the fuel, that heat should not get transferred. Through the surface to the outer environment, because in this experiment we need to determine how much amount of heat has been liberated during the combustion process. If that heat get absorbed by the outer body, then it's of no use here. Okay, so hence this copper metal or container, it is completely sealed by an insulator. So inside this we are placing a sealed bomb, okay, which is having an inlet, where we need to pass oxygen into it. Okay, it is also purely made up of double-sided stainless steel. It is purely made up of stainless steel, and this will be completely placed inside the copper container. Okay, and it is having an inlet where we need to pass oxygen through it, because to burn the fuel completely inside the bomb calorimeter we need to pass oxygen. Okay, so this bomb has been completely sealed. It has been completely sealed, and up to 25 degrees centigrade the initial temperature will be there, and inside that we are placing a crucible which is purely made up of platinum. Okay, this is how the crucible will be placed inside the bomb calorimeter, and in that a known mass of fuel, it might be a solid or it might be a liquid fuel, will be taken inside this crucible. Okay, a known mass. I am very stressing about this point. It's a known mass of fuel. Okay, so this fuel has to be ignited. Okay, so we can't directly, once you pass oxygen, the fuel will not get automatically ignited. We have to initiate that ignition. So to initiate the ignition, we are just connected this particular crucible with a pair of electric wires for ignition, and that has been connected through a battery where we pass electricity just to ignite this particular fuel which is taken inside the crucible. Okay, so now after that we are just filling this particular copper container with water. Okay, a known mass of water has been placed inside this, because the water body has to absorb the amount of heat liberated when the mass of fuel which is taken inside the crucible, which is placed inside a bomb, when it is ignited, the amount of heat which is released by the ignition of that fuel has to be absorbed by this water body. Okay, so now once the heat liberated, that has to be distributed throughout the water body which is present inside that. Okay, not just a part of water has to be heated here. So heat has to be uniformly transferred throughout the water body, and hence we are placing a magnetic stirrer. We are placing a magnetic stirrer here. Okay, so this stirrer, it mainly helps to stir the water continuously, so that whatever the heat that is liberated during the combustion process will get uniformly distributed throughout the water body. Okay, so next, the very important one is about the temperature. So before igniting the fuel which is taken inside the crucible, which is placed inside the bomb calorimeter, so initial temperature has to be noted down. So that's why we are just placing a thermometer, Beckman thermometer, inside this. We are fixing this thermometer. Okay, so inside this water body. Okay, so just to know the temperature, rise in the temperature, which is very important to know about the ignition process. Okay, so this constitute overall a bomb calorimeter. Okay, so this is about a very simple construction of bomb calorimeter. Once again, I repeat about the construction process. It is purely made up of copper. Okay, it is purely made up of copper vessel which is coated with insulated material. So I have already told why we are coating this copper vessel with an insulator at the outer surface area, because whatever the heat that is liberated during the combustion process, they should not be absorbed by the outer atmosphere or outer body, because we need to know how much amount of heat is liberated during the combustion process. Okay, next, apart from that, here these are the ignition rods, which are nothing but electrodes, which helps in the passage of electricity through the outer source, that is battery. Next, there is the presence of thermometer to note down the initial temperature T1 degree centigrade and the final temperature T2 degree centigrade. It's a very important operators which has been fixed into a bomb calorimeter. Next, this is the inlet where we are passing oxygen into the bomb calorimeter, and we call it as bomb calorimeter, which is purely made up of stainless steel, Okay, next there is the presence of crucible. crucible which is purely made up of platinum, and here there is a presence of mass of fuel, okay, known mass of fuel, okay, so which is taken as m. So here there is the presence of magnetic stirrer, which is used to stir the water body so that whatever the heat that is liberated will get completely distributed throughout the water body. Is it clear? So this is about the simple construction, a neat labeled diagram of bomb calorimeter. Okay. If it is clear, next we shall switch over to the next thing, that is about the working of bomb calorimeter, how it works. So if you just observe this construction itself, it gives a clear picture for you people how this bomb calorimeter works and how we can determine the GCV and NCV. Okay, so here the known mass of the fuel which is present inside the crucible. Okay, so for this we are supplying electricity through these electrodes just to ignite this fuel which is taken inside the crucible. And only in the presence of electricity the fuel will not get ignited. The major component which is required for ignition of any particular fuel is oxygen. It is oxygen. So we are supplying oxygen through the inlet which is provided into the bomb calorimeter. So when there is a simultaneous supply of oxygen, plenty of oxygen along with electricity which is passed through the electrodes through the crucible, this fuel starts igniting. Okay, once it starts burning, it starts releasing more amount of energy in the form of heat. So the released heat will be completely absorbed by this stainless steel body which is known as a bomb calorimeter, and once the heat has been transferred or absorbed by this bomb calorimeter, that heat will be transferred to the water body. So here the very important thing what we should know here is, before igniting the fuel, before passing the electricity through the wires to the fuel, first we need to check what will be the initial temperature of this particular water body. That we call it as T1 degree centigrade. We call it as T1 degree centigrade. So T1 degree centigrade is nothing but the initial temperature. It is nothing but the initial temperature. Okay. So once you note down the initial temperature T1 degree centigrade, okay, and once you know what is the mass of the fuel that has been taken inside this crucible, we consider as m. Okay, m, small m, is nothing but the mass of the fuel taken inside the crucible. Okay, so whose calorific value has to be determined. Okay, let it be a liquid or let it be a solid. Okay, in case if you consider a solid one, you are considering it in terms of grams or in terms of kilograms. If it is a liquid, you are considering that in terms of ml or cm cube. Okay, so only solids and liquids can be taken inside this crucible. That is, by using this bomb calorimeter you can calculate calorific value. Okay, so if this is clear, then we shall know what will be the further process that happens here. As I told you, people will be noting down the initial temperature, that is T1 degree centigrade, before ignition, and then once the known mass of the fuel is ignited in the presence of oxygen, when it starts burning, you know that fuel releases more amount of energy in the form of heat. So the released heat will be absorbed by the stainless steel bomb calorimeter, and that will be passed to the water body, and this water body starts rising its temperature when heat has been transferred from bomb calorimeter to water. Okay, so once there is a complete ignition, means whatever the fuel that we have taken has been burned completely, 100% combustion. Okay, once we achieve that 100% combustion, at finally, okay, we are determining what is the T2 degree centigrade of the water. T2 is nothing but the final temperature of the water body, because as the combustion process takes place, as the heat starts released during the combustion, the bomb calorimeter will be passing, or it will just increases or rise the temperature of the water body. As temperature of the water body gradually increases, because there's the presence of a magnetic stirrer here. So this magnetic stirrer helps in the movement of water molecules throughout the bomb calorimeter, and hence heat will get uniformly distributed throughout the water body. And finally, after complete combustion of this sample, fuel sample, we are considering what is the temperature that has been attained in the final stage. So that is T2 degree centigrade. T2 degree centigrade. So this is about working of bomb calorimeter. This is about the working of bomb calorimeter. Is it clear? Hopefully I am clear about the construction and working of bomb calorimeter. Next, the very important thing is to know about the equations to calculate the gross calorific value and net calorific value by using this bomb calorimeter experiment. Okay, so in this we know what is the mass of the fuel that has been taken, that is M. We will be knowing how much amount of water, that is the mass of the water that has been filled into the bomb calorimeter, which was initially determined, or initially we will be weighing that water sample, and then we are pouring into the copper container, and we know what is the initial temperature and what will be the final temperature after the complete ignition of the fuel which has been present inside the crucible. Okay, and by considering all these things, it's very easy to determine the GCV and NCV. If this is very clear, I will next switch over to the calculation part, that is the equations to calculate GCV and NCV. So till now we explained about the construction and working of bomb calorimeter. The next important thing is to know about the equations to calculate GCV and NCV. This is very important. It might be from examination point of view. Okay. So in case of GCV and NCV, as I told, how we define GCV and how we define NCV. So GCV is a gross calorific value or high calorific value, which is nothing but the amount of heat which is liberated when a known mass of the fuel is completely burned in the presence of oxygen, and the product which is released during the combustion process has been condensed back. So GCV contains the amount of heat liberated during the combustion process as well as the heat which is released during the condensation of the byproducts. And NCV, it is the net calorific value, where we are not considering the byproducts, because during the combustion process the byproducts are let off free to the atmosphere, and only we are considering the amount of heat released during the combustion of the known mass of the fuel. So hence GCV value will be always higher than net calorific value, and hence we call GCV as high calorific value and NCV as low calorific value. Hopefully this is clear for you people. What do you mean by GCV and what do you mean by NCV? So now we shall come with an expression to calculate GCV. What do you mean by this GCV? Gross calorific value. So gross calorific value, to calculate that, we are considering W plus small w. So what does this W means? It is nothing but the mass of the water which is taken inside the calorimeter. The mass of the water which is taken inside the calorimeter, because previously while explaining about the construction of bomb calorimeter, I told you people that we are just transferring the water into the copper container by knowing the weight of that water before transferring. So hence W is nothing but the mass of the water which is taken inside the bomb calorimeter, and small w is the water equivalent of calorimeter. Apart from that water, we are just placing the other components inside the bomb calorimeter, and apart from the weight of the water, whatever the weight remaining, the rest of the weight which are being produced due to the presence of these containers, so that we call it as water equivalent of calorimeter. Okay, so W, capital W, it represents the weight of the water, and small w, it represents water equivalent of calorimeter. Okay, and this will be multiplied by T1 T2 degree centigrade minus T1 degree centigrade. Okay, so what is this T2 and T1? As I have explained during the construction process and working, T2 is nothing but the final temperature, means after complete combustion of the fuel, whatever the heat that has been generated, so the generated heat has been transferred to the water body, and the final rise in the temperature of the water body will be noted down. We consider this as T2 degree centigrade. So T1 is the initial temperature of the water body, and that will be multiplied by S. What is this S? S is nothing but specific heat. Okay, why we are considering this specific heat means because in gross calorific value we are considering the amount of heat that has been generated due to the condensation of the byproducts. Okay, so during the condensation process, okay, the steam will be converted into water at 100 degrees centigrade, and during this condensation of steam to water at 100 degrees centigrade, the amount of heat that has been released, okay, so that will also be considered, and hence we are multiplying this by specific heat, that is S. Okay, so this overall divided by M. This overall divided by M. What is this M? M is nothing but the mass of the fuel. M is nothing but the mass of the fuel. Okay, so coming to the unit for calculating this GCV, as I know, okay, as I told, this W, okay, it is also in terms of kg. Okay, and this small w, that is water equivalent, that is expressed in terms of kg, and this will be multiplied by T2 minus T1 degree centigrade, okay, which is expressed in terms of degree centigrade here. Okay, let us not consider degree centigrade here. T2 minus T1 degree centigrade. Okay, that will be multiplied by specific heat. Specific heat unit is kilojoules per kg per degree centigrade. Kilojoules per kg per degree centigrade. This is overall divided by M. Small m is nothing but the mass of the fuel, that is also expressed in terms of kilograms. That is also expressed in terms of kilograms. Hence, GCV is nothing but W plus small w, which is expressed in kg, T2 minus T1, that is a rise in the temperature in degrees Celsius, and S is the specific heat. The unit for specific heat is kilojoules per kg per degree centigrade, and overall it is divided by the mass of the fuel which has been taken in a bomb calorimeter, which is expressed in kg. Okay, so here kg get cancelled, degree Celsius gets cancelled, and finally GCV, gross calorific value, is W plus small w into T2 minus T1 degree centigrade, T1, okay, that into specific heat divided by M, kilojoules per kg, kilojoules per kg, kilojoules per kg. So this is the expression to calculate GCV. This is the expression which is used to calculate GCV. So under this, what is W? Capital W means what? It is the mass of the water. Okay, it is the mass of the water taken inside the calorimeter, and small w, it is also the water equivalent, mass of water equivalent of calorimeter, and T2 minus T1 degree centigrade. T2 is the final temperature. Final temperature of what? Final temperature of water. Okay, and T1 is the initial temperature. initial temperature of water, okay, and T2 minus T1 we can just call it as capital T. So that is nothing but rise in temperature, okay, rise in temperature. Don't get confused, because in some of the textbooks they have directly given it as capital T, which is nothing but the difference between T2 and T1, okay. So next, m, small m, okay, m is nothing but the mass, m is nothing but mass of the fuel, m is nothing but mass of the fuel taken, okay. It is also expressed in kilograms, as I told, okay. And S is the specific heat, S is the specific heat of water, because we are condensing back the byproducts in case of GCV, and hence we are multiplying this by specific heat, okay. So this is the expression to calculate GCV, okay. Now we shall switch over to NCV. So what is the expression to calculate NCV? That is net calorific value, net calorific value. So NCV is nothing but GCV minus, because as I told in net calorific value or low calorific value, we are not considering the amount of heat which has been released due to the byproducts, because byproducts are let off free to the atmosphere. They easily escapes in the bomb calorimeter, and only the total amount of heat that is released will be considered. So that's why we have to subtract the amount of heat released by the byproducts. As I told, to calculate NCV, we know that the byproduct which is obtained during the combustion process, it will be water molecule. So if water molecule has to be released as a byproduct, that fuel has to contain hydrogen in it. So when hydrogen, carbon and oxygen, there the valence electrons being exchanged between these three atoms, then large amount of heat will be generated. So here, if the percentage of hydrogen which is present in that particular fuel is known to us, then it will be very easy to calculate the net calorific value. So as I told, if you want to produce one molecule of water, that is 18 grams of water has to be produced, means 9 grams of hydrogen is very much required. So here we are just subtracting this by 0.0, we are converted that into percentage, okay, which is multiplied by the percentage of hydrogen present in that particular fuel, which will be known to us, which will be given in any of the numerical problem. Okay, unless and until if he has not given the percentage of hydrogen, you cannot calculate the NCV, because we will be not knowing in that particular fuel how much amount of hydrogen is present. So that percentage of hydrogen is directly related to the amount of water molecule that has been produced. So we are just considering 0.09 into percentage of hydrogen into L. L is nothing but the latent heat of steam. Latent heat of steam. Okay. So unit for that is kilojoules per kg. Kilojoules per kg. So this is the expression which we use to calculate NCV. So hopefully it is very clear. NCV is nothing but GCV minus 0.09 into percentage of hydrogen present in that particular fuel into latent heat of steam, kilojoules per kg. So this is the difference between GCV and NCV. Okay, so here we have given the terms. What are these terms? Okay, in case of GCV and in case of NCV. Okay, in examination sometimes he may ask explain the construction and working of bomb calorimeter and derive the equations to calculate GCV and NCV. Okay, so up to here you need to write it. Is it clear?